How were engineers able to lift massive solid steel blocks weighing thousands of tons into the air, suspend them above the sea at heights of hundreds of meters, and connect them together with errors measured only in millimeters, all on a construction site constantly affected by the tides every day? And it was under exactly those special conditions that Japanese engineers built the Kesennuma Bay crossing bridge, a 3-span steel cable-stayed bridge with a main span of about 360 meters, serving as a key link on the Sanriku coastal route. More than just a bridge crossing a bay, it also stands as a symbol of how Japan rebuilt its coastal infrastructure with some of the largest and most precise engineering solutions in the world. And welcome to Mandarin Tech. In today's video, let's explore the art of super heavy lifting and break down each sea journey that carried steel across the bay to create the Kesennuma cable-stayed masterpiece. Rising from the ruins left by the 2011 Tohoku tsunami, the Kesennuma Bay Crossing Bridge is not just a simple transportation project. It is a vital link in the rebuilt Sanriku route. After the old road running along Kesennuma Bay was severely destroyed, engineers chose a bold solution to build a 3-span steel cable-stayed bridge straight across the entire bay, with a total length of about 680 meters and a cable system supporting the steel deck, stretching hundreds of meters below. This structure was designed not only for everyday travel, but also to serve as an emergency relief connection in critical situations. However, Kesennuma Bay is an important aquaculture area. To protect the marine environment, the engineers could not carry out large-scale underwater concrete construction in the usual way. Because of that, they fully fabricated massive modules onshore first. Then, giant floating cranes were brought in to carry steel blocks weighing thousands of tons out to sea and place them directly into position. To raise these massive steel spans into the sky, engineers first had to conquer the seabed. Construction of the superstructure could only begin after the entire foundation system and the underwater concrete piers had been firmly anchored into the geological base of Kesennuma Bay. At this point, the construction site entered a critical transition phase. Contractors began removing the temporary support structures and the Larsen sheet pile cofferdam system. In simple terms, these were steel walls driven deep into the seabed to block out seawater and create a dry working space, allowing engineers to pour the pier foundations right in the middle of the bay. Once this protective steel shell was removed, the massive pier foundations, especially the foundation of the main tower, Pier P12, finally emerged above the water surface, marking the project's entry into its most important construction stage. After the offshore piers reached their designed elevation and the construction platform was fully cleared, the project moved into the stage of erecting the main cable-stayed tower, the most critical structural component that makes the nearly 360-meter main span of the Kesennuma Bay Crossing Bridge possible. Because construction took place right in the middle of the bay and the time spent working offshore had to be minimized as much as possible, the tower segments were not fabricated on site. Instead, they were prefabricated onshore as large steel blocks. Each block was already equipped with stay cable anchor plates, connection details, and internal stiffening ribs before being transported to the erection location by specialized barges. At the site, heavy lift floating cranes lifted each tower segment from the barges and placed them precisely onto the tower base at the top of the pier. The erection process followed a bottom-up sequence. After each block was positioned, engineers carried out 3-dimensional geometric alignment before fixing it permanently with high-strength bolts and completing the final welding on site. Throughout the tower erection process, survey teams continuously monitored the vertical alignment of the tower axis. Even a very small deviation in the lower segments could create a significant error at the tower top, which rises about 115 meters above sea level. Thanks to this large block offshore assembly method, construction time for the tower was significantly reduced while still maintaining the geometric precision required for the next critical stage. Installing the stay cable system and extending the steel deck segments out toward the center of the bay. After the main tower reached its designed height, the construction site moved into the stage of installing the stay cable anchorage system, an important transition step before the steel deck segments began extending toward the center of the bay. This stage established the precise geometric axis of the tower before the stay cables started to carry real structural loads during the cantilever extension of the bridge span. At each designed elevation along the tower, the stay cable anchor units had already been integrated into the steel tower blocks during the onshore fabrication stage. Once the tower was fully erected, engineers carefully checked the positions of all anchorage points using a three-dimensional coordinate system to ensure they matched the intended geometric curve of the future stay cable layout. At the same time, the construction team deployed a real-time tower geometry monitoring system. Measurement instruments were installed at multiple elevations along the tower to track tilt, horizontal displacement, and accumulated deformation caused by the tower's self-weight, as well as the effects of wind and tidal movement. This control step was essential before tensioning the first stay cable bundles, because even a small deviation at this stage could change the trajectory of the main deck extension during the following erection process. In some cases, engineers carried out fine adjustments by modifying connections at the anchorage points or applying temporary corrective forces to bring the tower axis back to its exact designed geometric position. Thanks to this careful monitoring and adjustment process, the entire tower system achieved the level of geometric accuracy required to begin tensioning the first stay cables. Unlike viaduct bridges that rely on continuous supports underneath, the deck of the Kesennuma Bridge had to extend hundreds of meters across open space above the bay. The only way to solve this challenge was by using the balanced cantilever method. This is a typical construction technique for long-span cable-stayed bridges, allowing the structure to gradually extend toward the center of the bay without the need for temporary support scaffolding from below. Large prefabricated steel deck segments were first manufactured onshore, then transported to the erection site by specialized barges. There, heavy-lift floating cranes raised each segment into its design position and temporarily connected it to the previously installed deck section. Immediately after placement, the first stay cable bundles were installed and tensioned according to the design forces to carry the load of the new segment. The erection sequence was always carried out symmetrically across the tower axis. This means that whenever one segment was installed on one side of the tower, a corresponding segment was installed on the opposite side. This method helped maintain moment balance throughout the span extension process and reduced horizontal displacement of the tower under offshore wind and tidal conditions. At the same time as each deck segment was installed, the tension in the stay cable bundles was carefully adjusted step by step to precisely control the geometry of the entire structural system. From this point onward, every additional segment not only increased the bridge span length, but also changed the overall balance condition of the cable-stayed structure. As the deck arms gradually extended from both sides of the main tower toward the center of the bay, using the balanced cantilever sequence, the main load-bearing frame of the Kesennuma Bay crossing bridge slowly took shape above the water. This stage also served as the final preparation before the most critical moment of the entire project, the closure of the main span at the center of the bay. When the steel deck arms extending from both sides of the main tower had nearly reached the center of the bay, using the balanced cantilever method, the construction site entered the most critical moment of the entire offshore erection phase, the closure of the main span. This step completed the main load-bearing structural system, transforming the two independent cantilever arms into one continuous bridge span, crossing the entire Kesennuma Bay. Before the closure operation, engineers carefully adjusted the tension of the stay cables step by step to bring the two deck ends closer together according to the exact design geometry. This process had to account for several factors at the same time, including steel temperature, offshore wind conditions, and the accumulated elastic displacement that had developed during the earlier span extension stages. Once the geometric deviation was controlled within the allowable limits, the final closure segment was lifted by a heavy floating crane and placed precisely at the center of the span. This operation required extremely high accuracy because even a deviation of just a few millimeters could create residual stresses throughout the entire cable-stayed structural system. After the closure segment was permanently connected, the tension of the stay cable bundles was adjusted one final time to bring the entire main span into its designed working condition. From that moment on, the main load-bearing frame of the Kesennuma Bay crossing bridge was officially completed above the water, marking the most important turning point in the reconstruction of the Sanriku coastal transport route after the 2011 disaster. Unlike many other sea-crossing bridge projects where the construction zone can be completely isolated, the Kesennuma Bay crossing bridge site had to continue erection work while the water surface remained actively used for aquaculture and local marine traffic. Because of this, offshore heavy lifting operations could not be carried out continuously under a normal mechanical construction schedule. Instead, they had to be carefully organized into short construction windows that match the actual operating conditions of the bay. For this reason, the erection sequence of both the main tower and the main deck was designed around the use of large prefabricated structural components. This approach minimized the amount of time crews needed to work directly over the water and reduced the area occupied by offshore construction activities. Thanks to this construction strategy, the installation of the main span could proceed steadily while economic activities around the bay continued without interruption throughout the entire construction period. The Kesennuma Bay Crossing Bridge is not just a single sea crossing structure, it is an important link in the Sanriku Coastal Road, a coastal transport corridor rebuilt after the 2011 tsunami to restore connectivity across the entire northeastern region of Japan. This route was designed as a new strategic transportation corridor, replacing the coastal road network that had been severely damaged by the tsunami. Building the bridge straight across the mouth of the bay not only significantly shortened travel distances between the two sides, but also removed the region's dependence on the old coastal road, which was highly vulnerable to earthquakes and large waves. As a result, the Kesennuma area gained for the first time a stable, continuous, and safer transport connection for daily travel, local logistics, and especially emergency relief operations during future disasters. On a larger scale, the bridge also plays a role as part of Japan's coastal soft defense infrastructure network, where transportation systems are designed not only for mobility, but also as components of the country's rapid response framework for major natural disasters. But have you ever wondered how this massive tower, rising about 115 meters above the storm-exposed waters of the bay, was actually built? The process began with the fabrication of thick steel plates at a structural workshop. These plates were cut into their designed shapes using CNC machines, then curved to match the tower's cross-section, forming the outer shell panels of each tower segment. Next, these steel panels were assembled into three-dimensional modules using multi-layer welding techniques. Inside each segment, stiffening ribs and reinforcement plates were installed to ensure the tower could withstand the large forces transmitted later by the stay cable bundles. After completing the main structural frame, engineers installed the stay cable anchorage units directly into their exact design positions within the tower segments. These components required extremely high precision because they directly determine how forces from the stay cable system are transferred once the bridge begins to operate. Once the entire steel structure of each segment was completed, the tower modules underwent three-dimensional geometric inspections and ultrasonic weld testing before receiving protective anti-corrosion coatings suitable for the marine environment. Only after all fabrication and inspection steps were fully completed were the tower segments transported offshore, where they were assembled into the finished tower, rising more than 100 meters above the waters of Kesennuma Bay. From the ruins left behind by the 2011 Tohoku tsunami, Kesennuma Bay has now been reconnected by a steel lifeline stretching across the open sea. The Kesennuma Bay Crossing Bridge is not just a transportation structure, but clear evidence of how Japan rebuilt its coastal infrastructure in just over a decade after one of the most devastating disasters in modern history. Behind every steel span extending across the ocean lies a bigger story about engineering, people, and the determination to recover after catastrophe. If you enjoy exploring massive engineering projects like this, don't forget to like, share, and subscribe to Mandarin Tech to discover more impressive construction sites around the world.